In this video, I'll talk about probability and give you an idea about what probability is about. This is a pretty complicated topic. We can have a whole course about probability theory, really. So I'm going to only explain the basics behind it. But it is really important because all our statistical evidence is based on the ideas of probability. The p value literally stands for probability, right? The probability that we would observe some effect or more extreme, given that there was no actual effect in the real world. Now, in statistics, we always describe variables. Now, variables can be anything, right? It's usually like a column in your data set, and it can be anything, right? Your measure on happiness or loneliness scale or gender or really anything. If a variable can take on different values, that means that one person might have a different value than another person. We call this a random variable. And this is a really important concept in statistics. It's not random in the sense that it's like uncertain, like a dice roll, like you don't know exactly what will come out. Random means more that it varies across people. And it can take one or another value with some probability. Probability describes how likely outcomes of a random variable are to occur. So, for example, a random variable could be your score on happiness. Let's say you're happy or you're not. And the probability describes what's the probability that you would respond with I am happy, what's the probability that you would respond with I am not happy. We denote the probability of some event occurring with this notation, the capital letter P, right? And the lowercase letter p, that you know from the p-value, is derived from this notation. So for example, if we say P open bracket, this one here, the happiness score of 1, then we use it to describe the probability that someone would score a 1 on the happiness scale. And so maybe 20% of the people score a 1, then that probability is 0.20. The probability is always between 0 and 1. And so probabilities range from 0 to 1, and you could multiply them with 100 to get a percentage. That's often easier to interpret. It depends on what you like. It actually doesn't matter that much. So 0.5 probability corresponds to 50%. It just times 100. And one important law in probability is the law of total probability. That means the sum of probabilities for all possible outcomes of a random variable must equal 1. So something must happen. Right? So if you have a happiness scale, you should have some response, right? Or if you're measuring the gender, there should be, you should measure something, right? So all possible outcomes, if you sum all the probabilities, you should equal 1. So this means that 1 minus a probability is a probability of something not happening. And this is actually something that's really useful in probability. Sometimes we're not interested in the probability of something happening. Sometimes we're interested in the probability of not happening. So for example, what's the probability of someone not scoring a 1 or scoring higher than a 1 on happiness scale? That's 1 minus probability of someone scoring a 1. Now, with two random variables, it gets a little bit more complicated. And so, for example, suppose we're interested in two things. The student is very motivated, and the student gets a good grade. So we have M. So let's say M is the event that a student would be motivated, and G is the event that a student would get a good grade. It means you have two random variables, motivation and grade, and they can take different values. Let's say motivation can take yes motivated, no motivated, and grade can take good grade, bad grade, bad grade, or maybe A, B, C, right, etc. Now we can define the probabilities per variable. These we term marginal probabilities. They're termed marginal because if you make a 2x2 table, so let's say we have motivation and we have grade, and let's say we have high, low, and low, high, we can then describe each of these cells, the probabilities of something occurring. And here in the margins, we have the total probability. So this would be, let's say for example 0.2 and 0.8, that means that there's a 20% chance that you would get a low grade, regardless of your motivation. That's why we call this marginal, because it's literally in the margin of this table. Right? We use the same notation as we did before. Probability M, meaning the probability you get a student would be very motivated, and probability G, a student would get a good grade. You see actually the important part here, a random student. If you pick one student from your sample, is that student very motivated or is that student get a good grade? But we can also look at how these events relate to one another. Now this creates some interesting notations. Here we have P with two things in there, M and G. This is what we call the joint probability of a random student that is both very motivated and will get a good grade. Let's go back to our table. That would be this cell over here. How many people end up in that cell? We can also get the conditional probability that a random student will get a good grade, given that we know that the student is very motivated. And that's also a very interesting concept. So here we use this line here to indicate a conditional probability. And say, okay, this is the probability of getting a good grade, given that we know that the student is very motivated. So what do we do then? So we had our cell again here. We literally just cut out this part of the table. We only look at the students that are very motivated. And then we look at, okay, how much of these, let's say maybe this was like 0.40 and this was 0.10 and 0.40, for example. So then we divide 0.40 by the sum of this, 0.50, to get the probability that you were getting a good grade if you know that you're motivated already. We don't look at the other people anymore. All right, so we have these four concepts of probability: the marginal probabilities, so these two, the joint probability, and the conditional probability. Right, the marginal probabilities are probabilities of one variable taking some value. The joint probability is probability that a random student is both very motivated and will get a good grade, so two variables taking some value. And the conditional probability is probability that one variable would take some variable, given that we know that the other variable also takes some variable. Now, with this, we can get some very important rules of probability theory. And these are pretty important, especially they underlie a lot of these of the assumptions that we need later in this course. We're not going to do that much with probability theory. We're not going to do that much with calculation here with probability. But I do think it's important that you've seen these things before, sometimes. If two events are independent, and that means that the probability of one thing happening, given that we know that something else happened, is the same as the marginal probability. It's this equation here. What does that mean? It means that we don't have to look at motivation to understand grade better. Right? We don't expect that if we select only the students that are very motivated, that there would be a different distribution of grade. We expect that, let's say, if the top 20% students get a high grade, but not top, that's actually unreasonable. Let's say if the top like 70, 80% students gets a high grade, yeah. And if we only look at the very motivated students, and we still see that the top 80% gets a high grade, then that means that motivation had nothing to do with getting a high grade. Now that's actually something we don't expect to be the case here. We expect if you're motivated, your probability of getting a higher grade will be higher than if we don't know if you're motivated or not. Then another important rule of probability is this equation here. The joint probability can be obtained by multiplying a marginal probability by the conditional probability of the other event, given that we know already that this event occurred. This is an expression that shows up sometimes, and it can be very useful if you want to make some calculations. In addition, we can get this conditional probability. This is actually, right, we can rearrange this, right? We can basically move this to the left to get the following. So the conditional probability can be obtained by getting this joint probability and dividing it by this marginal probability. Okay, let's look at an example. So suppose we throw a coin 2 times. So we have 2 variables, coin 1 and coin 2. Right, so we have coin 1 here and coin 2. And suppose that the event is that coin 1, C1 indicates that the first coin lands on its head, and C2 indicates that the second coin lands on its head. Now, if this coin is fair, we know that the probability of landing on its head should be 0.5. or for one coin and for the other coin. Means you have a 50% chance landing on the head, 50% chance of landing on the tail, if it's a fair coin, and you can expect that the coin would be fair. We also know that these two kings are independent. This means that the probability of the second coin throw is not influenced by the probability of the first coin throw. Right, now this makes sense, right? If you think about it, but many people actually still don't really believe this. It's like if you throw, let's say, a coin 10 times heads, they think that the probability of getting a tail is higher, right? That's not the case. And you'll see, for example, with dice throw. So let's say you have a game. Let's say you have 2 dice. Yeah, and I throw the first dice and I get a 3. Then the probability of getting a 3 on the second dice is just the same, right? Oh, sorry, where's my 3 here? It's the same as if I did not know that the first dice was a 3. It makes sense because these are 2 different objects, right? Get 2 different dice now, but these are different objects. They're not influencing each other in some way. There's no magic here. And it's not like the rules of the universe are self-correcting in that way. That they say, okay, no, the probability should be on the long term 0.5. So after 10 times a heads, we should get a tail. That's not the case. It is kind of self-correcting in a way that if you would then throw an infinite amount of coins, at some point you're going to convert to 50% heads, 50% tails. But if you throw 50%, let's say you throw 10 times heads in a row, and you keep throwing and you throw after 1,000 times, then that's, yeah, those 10 times will not matter that much anymore. So these probabilities are independent. So that means that the probability of the second coin being heads is the same regardless if you know the first coin throw or not. It's 0.50. So now we can calculate some other probabilities. For example, what's the probability of throwing 2 times heads? Well, if you don't know the first throw, that's 0.25. Why? Because the joint probability equals, when we look at our previous slide, this expression here, joint probability equals the marginal probability of 1 times conditional probability. But this one, we know from here, is just its marginal probability as well, because they are independent. Now this is a extremely important thing in statistics actually. Like any model that we're going to use, we're always going to talk about the assumption of independence. And that comes from this. Basically, we're modeling your probability of getting a response for subject 1, for subject 2, or for you and for someone else. And we're trying to model their joint probability. So we get basically this, we don't get this, we won't see this, but under the hood this happens. This joint probability for all our responses. We can only get that if we can reasonably multiply their marginal probabilities under the assumption of independence. That means that we should assume that my responses are not influenced by my neighbor or the person next doors or the other people in the survey, that there's no clustering, for example, in there. If that's not the case, then actually this formula doesn't hold and we're doing something incorrect. And then software will still work, you get a result, but it's not the actual probability, and that could be problematic. It's a small detail, but you'll see it sometimes, the assumption of independence, and this is really where it's coming from. Now what's the probability of not throwing 2 times heads? That's 1 minus this joint probability is 0.75. That's easy to calculate here. We just need to multiply these 2 things 2 times. And then we do 1 minus that, or we take this complement. All right, and now I have a thought experiment. What is the probability that 2 people, let's say we have a tutorial class of 20 or a course of 180 students. Okay, what is the probability that 2 people in a class of 20 students share the same birthday? And what about a course of 180 students? If you have 180 students in a lecture theater, what's the probability that 2 of these, any 2, share the same birthday? Now, maybe pause the video for now and think about it. If you can, try to calculate it, but it's a pretty hard calculation, so you don't have to try that. Just think about it, what you would expect the probabilities to be. All right. So let's look at the answer. Now, before we calculate this, we actually need to make a few assumptions. This is actually something that's hard to calculate if we don't make these assumptions. Right, so I'm saying assuming here. What is an assumption? An assumption is something that we are basically assuming to be true to make the calculations work. And the interesting thing about it is that assumptions are not actually often true. But if we look in the real world, it might be not really possible to compute. So we can make a very straightforward calculation here under some assumptions. But if we don't take those assumptions, it will be a very, very, very hard calculation that we can't do. So the main assumption that I have here is all birthdays are equally likely and nobody has a birthday on February 29th. And independence between people. Meaning no twins in the data. Okay, if you I think mostly twins here in this case. People that are sharing the same birthday because they are genetically related. Right? So what does it mean, these assumptions? Assuming all birthdays are equally likely. This means that I assume that on every day of the year, there's an equal probability of being born. That is actually not the case. There are seasonal trends. I don't actually know the trends, but I know that there's some months where more babies are born than other months. So yeah, to do this calculation properly, you would actually need that data to get the probability per day of being born, because there definitely are some seasonal trends there. Second assumption, no birthdays on February 29, no leap years. Why? Well, otherwise, again, it would be very hard assumption, and I would need to calculate, okay, so I have 20 students. Let's say this cohort, usually, except for example, the NUS, the students are of certain ages, right? Like maybe this is a first year course, then you have like 18 or 20 years old, right? Or a second year course. Then you have to calculate, okay, so was there a leap year like 18, 20 years ago? Yes or no, etc. Makes the calculation much harder. We probably can assume that it doesn't matter that much for the calculations. The number won't be that different. So let's assume no birthdays. And independence between people. So these are assumptions I make. Now, we always make assumptions. And that's when we mention that in analysis, we for example, assume normality. We do that because we need to make the math works. Its assumption is not true. The math technically doesn't work out, but it could still be a good approximation of reality. Okay, so let's make these assumptions, right? And then let's take the probability that two people do not share a birthday. So the probability that two people do not share a birthday is 364 over 365. Why? Let's take one person. This person's birthday is any date of the year. It doesn't matter. And then we take the second person. And then we see, okay, is that person born on the same day? Well, there are 364 days in a year, excluding leap years, where that is not the case, and one day in a year where it is the case. So we get 364 events where it's not the case, one event where it is the case, and that gives us the probability of 364 over 365. Very small, right? Or very high actually, but the complement is very small. Now, if you think about it more, let's say add third person, right? So let's say we have person 1. The birthday is any day, let's say January 1st. And let's say we have person 2. And let's say that person is born on a different day. Let's say January 2, for example. Then there are only 363 days left. For the fourth person, only 362 days left. For the fifth person, only 361 days left. Etc, etc, etc. Now we can multiply these probabilities. For one person, for two person, for three person, for example. And then we can take the complement to calculate the probability that people do share a birthday. Right? So we have here probability that n people do not share a birthday is the probability that 2 people don't share a birthday times probability that 3 people don't share a birthday times probability that 4 people don't share a birthday, etc. And the probability that at least 2 people do share birthdays is 1 minus this number. So what do we get? It's actually really interesting. If you calculate this, it starts low, obviously, but it goes up really, really, really fast. The probability that 2 people share a birthday in a class of 20 students is 41.1%. 41.1%. That's Really incredible, right? You would not expect it. Of course, that is under these assumptions, but that's a really high number. The probability that two people share a birthday in a class basically approaches 1 from like 80 people or so. So very, very, very likely two people taking this course are sharing a birthday on the same day. It could be any two people, of course, you don't know who, but yeah, that's very likely the case. You would not expect this to be so high. But maybe in your tutorial, try to figure out if two of you have the same birthday, right? Maybe you can throw a party, maybe it's even on one of the tutorial days. Well, that probability, of course, is a bit lower. Okay. Now, last thing I want to talk about in this video is actually the term probability. Because you think that probability is something that's clearly defined and everybody agrees on what probability is, but that's actually not the case. Like, people actually disagree on this concept probability already. And if you disagree already on what probability is, and everything that follows afterwards, you're also disagreeing on that. There are two main interpretations that I'll talk about, a few more, but these are the main things. The classical interpretation and the Bayesian interpretation. And they can conflict quite a while, actually. In classical or frequentist statistics, we interpret probability as a long-run event, frequency of an event happening. So if you have the p-value, the p-value is a classical frequentist statistic. Its interpretation is frequentist. The p-value of 0.01 means that we expect to find a test statistic at least as extreme in 1% of the samples of the null hypothesis being true. So that means in a hypothetical case that we would repeat our experiment 1,000,000 times, in 1% of those, if the null hypothesis is true, there's no actual effect, we would get a p-value of 0.01 or lower. The Bayesians, they view probability as a subjective degree of belief. So they see probability as a probability that something is true or that something is not true. That is a very different concept. So in the frequent statistics, we're looking at the repeated observations and seeing, okay, if we would repeat this, how often would we find something? In the Bayesian setting, we quantify it as degree of belief. Right. So for example, here we have this XKCD comic, which is a really, really fun website with lots of very nerdy comics like this. And this one says, okay, this neutrino detector measures whether the sun has gone nova. So this is like a machine, and it measures if the sun exploded. Then it rolls 2 dice. All right, so let's take 2 dice here. 2 dice, and it rolls them. If both come up with 6, in this case it didn't happen. If both come up with 6, it lies to us, otherwise it tells us the truth. Okay, so the probability of 2 dice getting 6 is 1/6 times 1/6. That is 1 in 36 thing, so less than 20%, less than 5%. Right, so this calculation. So now the machine says, okay, yes, the sun has gone over, the sun exploded. Then the frequent statistic would say, okay, well, this result would happen by chance, only 1 in 36% times. In this case, when both dice rolls were 6. So that's less than 0.05, so I concluded the sun's exploded. And then the Bayesian says, I bet you $50 it hasn't, because the Bayesian basically has a degree of belief. Basically, the Bayesian also takes into account that there is a priori belief that, yeah, okay, this is super unlikely to happen that the sun would explode. So even though the probability under chance is low, 0.027, right, so 1 in 36, because there's only one probability of 6 2 times, even though the probability of something occurring under chance is low, the Bayesian would still not believe that the sun has exploded, because the Bayesian has a priori belief. Now the frequentist can't really take this a priori belief into account. There's actually a lot to say about this, and I don't want to make this video much longer now, but I'll talk more about this at the end of the course in week 13, when I talk about Bayesian statistics. But basically, if you adhere to the Bayesian view of probability, you actually can't do these frequentist analysis. They don't really make sense. And so for the frequentist, for example, we look at the p-value, right? So p equals the probability of the data given that we know that the null hypothesis is true. And in the frequentist setting, the null hypothesis is either true or not. There's not like a probability of the null hypothesis being true or the probability of the null hypothesis not being true. Because the null hypothesis is just true or not. It's not going to be true sometimes and not true some other times. And it's like either there is an effect or there's not an effect. And then they talk about, okay, if there is an effect, if we do 100 experiments, how often would we find it? That's your statistical power, which I'll talk about later. If there's not an effect, how often would we still find an effect? That's your p-value. That's how the frequentist thinks. The Bayesian, because the Bayesians believe in a degree of belief, or they see probability as a degree of belief, they can talk about the probability that a hypothesis is true. So they can say, okay, I am interested in the probability that the hypothesis is true. So what the Bayesian is interested in, the Bayesian is not interested in this. The Bayesian is interested in this. What is the probability that a hypothesis is true given that we know our data? Where the frequentists cannot really look at this because it doesn't make sense. A hypothesis is either true or not in a frequentist setting. The Bayesians, because they can use probability as a subjective degree of belief, they can think, okay, I think I have 80% certainty that the hypothesis is true or not. But the hypothesis is true or not. Like it's 0 or it's not 0. Okay. This completely changes everything. And this makes it that if you really adhere to the Bayesian perspective, it doesn't really make sense to do the p-value. You can do something better, like this posterior probability, or actually what they will do is the base factor, which is something I'll talk about later, but this is like the Bayesian version of the p-value, which is not taking your prior expectation of the hypothesis in mind. And I'll talk about it in week 13 later. And that's nice, and it's actually a really cool thing to do. The only problem is that this is also a bit harder and in part subjective, because this probability here depends on your prior belief and actually some other subjective things as well in the data. We have a subjective belief on parameters, for example, that we need to take into account as well. So computationally it's hard to do, and it's in part subjective, where the frequentist statistic will always give you the same result. And a lot to say about that. I'm going to talk about it more. We're going to adhere to frequentist statistics for the most part of the course, because that's what most people do in psychology especially. But I'll definitely talk about Bayesian as well, especially because we are going to use the program JASP for this course. Now JASP is made by a great team of researchers from Amsterdam, where I used to do my PhD as well. And they made this really awesome free program that, yeah, in my perspective, just completely replaces SPSS in psychology. It does everything we need to do in psychological research and more. And it's free to use, and it's nice. So yeah, that's really nice. But the reason why the developers actually developed JASP originally was to have a Bayesian alternative to SPSS, to allow you to do base factors, the Bayesian alternative to the frequentist tests that we do, like a t-test and ANOVA regression analysis. But it's also designed to have the classical test in there, so it has both the classical and the frequentist, both the classical and the frequentist statistics. And that's because, yeah, so we can use it in courses like this, right? So the way they describe it is actually, it's like a Bayesian Trojan horse. Like you use it, you get used to it, you do your research with it, and then there's a button with Bayesian t-test. Maybe you press it at some point. And the moment you press it, you're a Bayesian. And you think, okay, this is really cool. And maybe you want to press the Bayesian ANOVA button, right? It's there, you can use it. That's how they describe it. They really like Bayesian statistics, so there's lots of other materials about it. There's this book that you can download for free, Bayesian Thinking for Toddlers. It's great. I read it to my 4-year-old quite often. He loves it because there are dino pictures in there. It's nice. You can download it. It's free, available online. That's it for this video lecture.